Welcome to the Proton Guru video practice for topic 7.7. These problems will give you practice on the basic type of problems in interpreting proton NMR spectra. Some brief and straightforward reading to get you ready for these types of problems can be found in the Organic Chemistry 2 Primer 2019 by Professor Houjeiry and coworkers. You can also find additional chemistry videos and information on how to match the videos up with your particular course textbook at protonguru.com. Some key study aids to help you with these types of problems are found in lesson 8.1.4 in the primer. The questions in this video are very reflective of the type of questions you'll see on multiple choice organic chemistry exams, including standardized exams. Which molecule produces the proton NMR spectrum provided below? Now there are several ways that you can approach these spectra, and I like to think about the different types of information that we can get from a proton spectrum as I look at a problem before I begin. The important pieces of information you can get from the NMR spectrum are the number of signals in the spectrum, the integrations of those signals, the multiplicity of each signal, and the chemical shifts for the signal. In a multiple choice problem, I'm always going to start with looking at the number of signals I should expect to get. For this first possible answer choice, I should get 4 signals. But I only have 3 resonances in this particular spectrum, so I can rule that out. 1, 2, 3, that's still in the running. 1, 2, 3, 4, 5 sites with protons on them. That should give me 5 signals. There's no symmetry in this molecule. Rule that out. 1, 2, 3, 4 different magnetically unique sets of protons should give me 4 signals. So in this particular case, I can use just the number of signals I expect for each molecule to determine that only molecule B could have given me the spectrum. So now let's apply the same logic to the next problem. If we take a look at how many signals we would expect to see in the proton NMR spectrum for each of these molecules, we see that we would expect 4 for choice A, 1, 2, 3, 4 for choice B, 1, 2, 3, 4 for choice C, 1, 2, 3, 4 for choice D. And that's what we have here. So looking just at the number of signals does not really help us. So we'll go one level deeper. We'll take a look at the expected integrations. This is a CH3. That will give us an integration of 3 for 3 H's. A CH2 will give us a signal that integrates as 2, another CH2, and another CH3. We would expect a 3, 2, 2, and 3. But there's only one of these signals that integrates to 3, so only one of these is a CH3. The other 3 are CH2 units, probably. This allows us to rule out choice A as a possibility. If we look at choice B, that CH3 would integrate to 3. The integration here would be 1. Well, we don't have an integration of 1. These numbers printed at the top are the integrations, so we can rule out choice B. Choice C, just like choice A, has 2 CH3 units, but our integrations only have 1 signal integrating to 3, so we can rule out choice C. So let's check choice D. CH3, CH2, CH2, CH2. We'd expect peaks integrating to 3, 2, 2, and 2. And that's exactly what we see. So compound D is the only one consistent with this NMR spectrum. Well, let's try another one. If we check how many signals we would expect for each of these choices, we have to be cognizant of the possible symmetry. For example, the symmetry plane here means that these 2 CH2s are equivalent. That will give us 1 signal for those. These 2 CH3s at the end are also related by symmetry. We should only get 2 signals if compound A were giving us a spectrum. In this case, we can rule it out because we have 4 signals. Compound D also exhibits symmetry along this plane. That means that this CH3 and this CH3 are identical to one another, and this CH2 is identical to this CH2, or equivalent to it. We would again only see 2 resonances for that type of molecule. Compound B is almost symmetric, but you see this is a methyl group, and down here you have an ethyl group. So this is not symmetric. So let's take a look at this. Each of these sets of hydrogens will give us 1 signal. CH3, a second one for CH2, another CH2, and a CH3. So we get 4 signals, and they should integrate to 3, 2, 2, and 3. Well, that's what we have, so B is still in the running. Let's look at choice C. 3, CH2, CH2, and another CH3. Alright, so B and C are still in the running. They both have the correct number of signals, and they would both have the correct integrations. So next we have to look at the multiplicities. Let's say we have compound B. Well, if we have compound B, this set of hydrogens would give us a singlet because no H's on neighboring carbon. Here's another CH2. Neither of its neighboring carbons has any hydrogen, so that would also be a singlet. Well, we only have one singlet. The other ones are triplets or more complicated multiplets. So we can rule out choice B, and hopefully choice C will match. This carbon with the 3 hydrogens is adjacent to an O, which has no hydrogens on it. So this will give us a singlet. All right, singlet integrating to 3 is consistent with a CH3 that should give us a singlet. Here's a CH2. That's adjacent to a carbon with 2 hydrogens. So the multiplicity is that 2 neighboring H's plus 1 is 3. That should give us a triplet. And we see a triplet integrating to 2. Next we have a CH2, and it's adjacent to both a CH2 over here and a CH3 on this side of it. So that multiplicity equals all 5 of those plus 1 should have 6 little peaks. 1, 2, 3, 4, 5, 6. Again, consistent with the structure. Finally, we have the CH3 all the way on the end. It's adjacent to a CH2. So the neighbors is 2. Multiplicity is number of neighbors plus 1 is 3. That give us a triplet. 1, 2, 3 little peaks. All the data are consistent with that structure. Now let's look at a fairly tricky problem, but one that's been featured in various forms on different standardized tests over the years. If we look at all these different choices, you'll find that each of them has a methyl group and an isopropyl group, and something else in between separating those two groups. But because of that, each of these compounds would have 3 signals in the proton NMR spectrum. One for a methyl group at the end, a second signal for the CH that's stuck between the 2 methyl groups. 2 methyl groups, of course, are the same as one another because you can rotate around this single bond. So you'd have a third signal. And that's true whether the methyl groups are attached to the C double bond O or directly to an O, etc. So all of these possibilities should give us 3 signals in the proton NMR spectrum. Likewise, if you think about the integrations, all of them have a methyl group. And then there's the 1 H on the CH group there. And then, of course, the 2 methyl groups on the isopropyl units will give you a signal for 6, regardless of which molecule you're looking at. So the integration doesn't help us either. Even the multiplicities won't be able to help us in this case. Each of these methyl groups is next to a carbon with no H's on it. So each methyl group, regardless of which molecule we look at, should give us a singlet. Every CH unit, regardless of which molecule we're looking at, is in between 2 CH3 units. So it has a total of 6 H's on neighboring carbons, so it should be a septet, should have a multiplicity of 7. And then each methyl group in an isopropyl unit, regardless of which molecule it's in, is next to a CH, so it'll always give us a doublet. And of course the spectrum has a septet, a singlet, and a doublet. So we can't use the number of signals, the integrations, or the multiplicities to help us figure out which of these 4 compounds might give us the spectrum. The only way we can tell them apart is by using the chemical shifts. What you'll see is that the septet integrating to 1, some type of CH unit, and we know the CH unit is in an isopropyl group in this particular example, that is the one that has the highest chemical shift. That means that that carbon is the closest to an electronegative atom. In this case, that means that this CH is directly bonded to an O, the only electronegative atom we have in these examples. So you could have this one where the CH is bound directly to an O, or this one where the CH is bound directly to an O. But in choice C, the methyl group, the CH3, should also be bound directly to the oxygen. That means it would also be way down where you expect an atom directly bound to an electronegative atom to be. But in our case, the methyl group, the CH3 signal, is way down at 2, so it can't be C. And in B and D, the CH is not directly attached to the oxygen. That allows us to use our knowledge of chemical shift to figure out that choice A is the only molecule that could have given us the spectrum.